On the graphene show will be Christianson from the University of Kansas. He did his RU work at Cornell and has taught an experimental and theoretical investigation of ultrasound transmission in Bubbly PDMS Phononic crystals.
All right, so good afternoon. Today I'd like to talk to you about phononic crystals. So phononic crystals are metamaterials made of two or more different materials with different acoustic properties. And when you arrange these in a periodic array, you can get some interesting and unexpected acoustic effects. So one of the first experimental realizations of phononic crystals was in this sculpture on the left, which is in Spain. And it's a 2D array of hollow steel rods. And scientists measured the transmission of sound through the sculpture and actually realized that due to destructive interference, it blocked low-frequency sound. In the center, we have another interesting application of phononic crystals, and that's in the understanding of whale and dolphin bubble nets. So it's been known that whales and dolphins will circle a school of fish while releasing a stream of bubbles, and then the fish will stay schooled inside the center. So Leighton realized that the reason why these fish stay inside instead of swimming away is because the sound of the whales outside of the ring of bubbles is actually confined to the ring, and as the fish go near the perimeter, they hear the whales, and so instead they prefer to stick to the center until they're gobbled up. On the right-hand side is a paper that was just released last month, and it is an air-transparent soundproof window. So there are holes in the window that allow air to pass through, but because of the arrangement of the holes, it actually blocks low-frequency sound, for example, from construction or from traffic. So our motivation was based on this paper from 2009 in which this group made a crystal out of PDMS and air bubbles. So PDMS is an interesting material because it has the same acoustic properties, or similar acoustic properties as water, but with the added advantage of since it's a gel, you can actually control the size and orientation of the air bubbles, whereas with water, it would just float away. So on the top left is a 4-layer crystal cross-section, and on the top right is a top-down view of 2 layers of their crystal. And then on the bottom is a frequency sweep between 0 to 5 megahertz. And the top black line is a single-layer crystal, and then the red line is a 4-layer crystal like what the cross-section is showing there. So what we see is a drop in transmission right around 0.5 megahertz, where the crystal is actually blocking the sound. So one of the challenges of this paper is that they had trouble aligning the layers of the crystal. As you can see in the top right image, there's a severe offset between the 2 different layers. In fact, the authors of the paper described aligning the layers as a problematic issue. So our objective is to understand the key parameters that govern transmission through these crystals. So we wanted to improve the alignment of the bubbles. We also wanted to change the shapes and the separation of the bubbles to see how that changed the transmission, and then also see how the transmission changed as a function of the layers of PDMS. So we began by using 2 theoretical models to fit their experimental data. The first is an iterative analytical model which treats each plane of bubbles as a partially reflective layer, and then models the transmission through each layer. And that's based on the equations on the bottom of the screen. The second method is based on multiple scattering theory, which is a more rigorous method that also treats each bubble as a point scatterer for the incoming waves. So now that we have a theoretical model, we want to investigate a broader parameter space, like by changing the bubble radius and the separation. So if you look at this top line on the left-hand side, that's the transmission for a single layer with a fixed radius and a fixed separation. And the radius here is 39 microns. So on the next plot, we're actually going to change the radius from 0 microns, which is no bubbles, all the way out to 100 microns, which is a lot of bubbles. So on the left is a surface plot, which kind of shows the transmission change as we go from 0 radius to 100 micron radius. And as you can see, as the bubbles get larger, the position of the block frequency shifts to the left, and the stop band gets wider. Another question that came up during one of our previous presentations was whether or not we could actually tune the crystal to block specific frequencies, and we found out that we can. So on the left is the blocked frequency as a function of bubble radius, and we found that it follows something called the Minnaert resonance, which is the natural resonance for a single air bubble. What's interesting is that with phononic crystals is that when we put these bubbles in a periodic array, we can actually tune the resonance away from the natural resonance of the crystal, which is the plot that you see on the right. So now that we have theoretical models for the crystal, we wanted to go ahead and build the devices. So we used contact lithography to pattern pillars on a silicon wafer, and then we etched the wafer down to a desired height, and then we spin-coated a PDMS on top of the pillars, and then peeled it off for ultrasonic transmission. So the top right image is the CAD of the pillars that we used, and then the bottom are SEM's scanning electron microscope images of the pillars before we put PDMS on it. So after we made the crystals, we wanted to go ahead and measure them. So on the top right is a cartoon of our experimental setup. So we have a transducer that sends an ultrasonic transmission through the crystal, which is the spot in the middle, and then we pick up the transmission on the bottom with a receiving probe. On the right-hand side, we have our first ultrasonic measurement of a single layer crystal. And while we still have some work to do on optimizing the measurement and the signal processing, the overall trend is what we expected. So now that we have an experimental setup and a single layer crystal, we wanted to tackle the alignment issue. So here's our workflow for making the crystals, and the items in red are some of the issues that we came up with aligning the two different layers. The biggest one is getting the position between the two different layers to line up, and then second is getting the layers to stick once we had them perfectly aligned. But with the help of the CNF staff, we were able to overcome each of these issues. So on the top left is a micrograph, a top-down view of our two-layer crystal with no visible offset in comparison to their two-layer crystal, which has a very strong visible offset. And then we went ahead and measured the ultrasonic transmission through that crystal. And once again, we have some work to do on fine-tuning our measurement process, but the overall trend is what we expected. So in summary, we used theoretical models to scan a broad parameter space for phononic crystals. We built single and two-layer crystals, and we also were able to demonstrate better alignment than previously published work. And finally, we measured the ultrasonic transmission of the crystals and found them comparable to our theoretical models as well as previously published data. So our future work will consist of changing other parameters such as the bubble radius to see how that affects the transmission, to see if it will actually fit the theoretical models like we have on the left. And then we'll also work on using our contact aligner setup to build thicker crystals of more than 2 layers. And we'd also, now that we have an ultrasonic setup, we'd like to measure other materials as well. So with that, I will take any questions.
Okay, so questions for our speakers. Yes?
In what way can these phononic crystals be incorporated in an application?
Yeah, so the question is, what are the applications of these phononic crystals? So one of them is in soundproofing. So you can make a crystal that will block a certain frequency and cover a wall or a surface with it to actually block sound. Another application is like coating submarines or boats, so that way they're invisible to sonar.
A cloaking device. Yes. Any other questions? Okay, that's thanks.